Welcome to Risk Awareness Week 2019. Presentation today is going to be on the state of the art in quantitative risk assessment. This is session 2. We've already completed session 1. And this one is going to be about the thinking, the math, and the coding involved in a state of the art quantitative risk assessment. My name is Mark Powell. I have been working in risk project management for almost 50 years now, and have been through a lot of different projects, and I'm wanting to share with you some techniques that I think will help you in your job. If you've not seen session 1, I strongly recommend that you go back. We will do a review of session 1, but if you haven't seen it, I strongly recommend that you go back and watch the replay of session 1. In session 1, we talk about the philosophy and framework to discuss quantitative risk assessment. And those concepts are really pretty important. And I think they're valuable. They would be valuable to you regardless to help you whether they necessarily are required for this in the subsequent sessions or not. I think it would definitely be of value. So session 1, we covered the philosophy and framework. We talked about a lot of abstractions of risk such that they're understandable to everyone who works in risk, no matter what their field, whether they're in science or engineering or whether they're in safety. And the point is, we really want to we talked about what the difference is between a qualitative and a quantitative risk assessment. Now this session, session 2, we're going to talk a little bit about the thinking. I'm not going to go directly into thinking, but you will see the thinking in the process as we go through this session. We'll talk about some mathematics. To really do a quantitative risk assessment requires some math. It's not hard math. Nothing that you will not have if you're in a position where you are interested in this subject. And there's some code that's going to be needed to perform state-of-the-art risk assessment. Now, this is not a tool that I'm selling or anything. This is code that you have to write. And one of the dark and dirty little secrets that I will reveal to you, I'm revealing to you early, is that every single problem is unique and is going to require unique code to solve. That means somebody's going to have to be doing some coding. But we'll go through the algorithms, and they're pretty easy to implement in code. The third session, we're going to go into a set of processes to actually perform a state-of-the-art quantitative risk assessment. And then I'm going to give you some real-world examples. Those real-world examples will include things that are outside that we normally face, outside the actual quantitative risk assessment itself. But I'm going to show how you can actually solve the problem and get a good decision made using a state-of-the-art quantitative risk assessment. So that's where we are. We are in session 2. We're going to talk about the thinking, the math, and the code to perform a state-of-the-art quantitative risk assessment. Just some review from session 1. If you haven't had a chance to look at the replay, this will allow you to at least follow until you can watch the replay. Qualitative risk assessments use guesses. The distinction between a qualitative risk assessment and a quantitative risk assessment is that a qualitative risk assessment uses guesses. And of course, guesses are assumptions, swags, expert opinion, etc. Those are all guesses. Even though we use numbers, that doesn't necessarily mean that the risk assessment is quantitative. I have seen numerous times people think they're doing a quantitative risk assessment when all they're doing is trying to come to a concurrence on opinions to pin the tail on a risk matrix that uses numbers rather than, say, some nebulous term. That's not a quantitative risk assessment. Quantitative risk assessments don't use guesses. Now, this is a point of contention with a lot of people. They just don't believe it's possible. But it is possible to avoid all guesses. Quantitative risk assessments can be cheaper than qualitative. That's a dirty little secret a lot of people don't realize or acknowledge. If you think about what goes into one of these large group sessions with senior people, say 20 to 50 in a room for perhaps 8 hours or multiple days, where you hire an expensive risk consultant to facilitate for you, is going to charge you travel and everything else. almost any quantitative risk assessment, state-of-the-art quantitative risk assessment, can be performed in a couple of hours. It may take longer than that to produce the presentation involved, but it could be performed in about a couple of hours of labor of someone who actually knows it. They can be easier to accomplish than qualitative. I don't know about you, but in some of those group sessions trying to pin the risk on the matrix, I have wanted to pull my hair out many numerous times. So it's sometimes easier to do as well. And the other thing is that a quantitative risk assessment really gives us, a state-of-the-art quantitative risk assessment, gives us at every point in time in the future the probability that some outcome level or above or outcome level or below will be realized for every possible outcome level and at every possible time. When we have that complete suite of all of those probabilities, we can truly make an optimal decision. We can find the optimum, and then we can apply our values and make excellent decisions. What that really does for us more than anything else is it saves resources. Complete quantitative risk assessments provide, as I mentioned just a second ago, for every time point in the future, probabilities for every possible realizable outcome, or worse or better. And up until the mid-1990s, it turned out that it was impossible to do a state-of-the-art quantitative risk assessment. Actually, just a quantitative risk assessment. We were forced to do qualitative risk assessments. We could not solve these problems. It turned out that just the analytical setup of a quantitative risk assessment produced an analytically intractable problem. Couldn't integrate the integrand. Probability density function is always in our integrand that we have to integrate to produce probabilities. But in the mid-1990s, there were some numerical methods that were developed that allows us to solve it. We'll talk about those today. Let's talk about the math. As I mentioned before, second year, to do a state-of-the-art quantitative risk assessment, it's going to require burning some calories above the neck because you have to do a lot of analysis of the problem. You have to do that anyway, even for a qualitative. You have to understand what causes the outcomes to occur, what causes them to occur at certain levels and at certain times, as well as the sensitivities, what they're sensitive to. If you don't discover those things, you can't do anything about it. But we're going to talk about the math involved, not so much in the modeling of those causal things, but the math involved of actually producing the assessment. Once you've done that engineering assessment, I call it an engineering assessment because to me it is engineering. Whether you're in the finance sector or whatever, you're engineering what those relationships are. To start with, let's revisit the probability axioms. They're really quite simple. There's 4, and we're always looking at propositions A and B, and I'm going to throw in something here, H. I talked about this earlier in the first session about how there's always conditional information involved in any time we have a probability. Axiom 1 is simply that probability ranges between 0 and 1. Real simple. These axioms are very simple, but they're very profound. Axiom 2, if something is true, the probability is 1. That's what we define. Axiom 3, this is the total probability law. The probability that A is true and the probability that A isn't true has to be 1. So the total probability is 1. And axiom 4, the comma means and. You'll notice that the bar means given. We covered that in our notation in session 1. The comma means and, the Boolean and operation. Probability of A and B given H is equal to the probability of A given B and H times the probability of B given H. And because of the commutability of the Boolean and operation, we can swap the B and A, and that gives us the probability of B given A times the probability of A. The H there, interesting story, Sir Harold Jeffreys kind of defined for us or established for us that every probability calculation is conditional. And he wanted to use I for information, but Fisher had already beat him to it with using I for his information matrix. So Sir Harold Jeffreys went back a letter, just like we went back a letter from IBM in 2001, A Space Odyssey, and had the computer named HAL, H-A-L. So we went back to H for that information that is always, there's always some conditioning on our probabilities. And that's the reason why we have it here. We generally, and you will see later in the presentation, that we don't always include H just for notational convenience, because sometimes our expressions get large. These four axioms for us, which are very, very simple, define the entire probability calculus. They also define all of probability theory. Everything in probability theory adheres to these. Okay, very, very simple. They are the basis for all of our uncertainty models. These are probability density models. Now, let's talk a little bit more about axiom 4. Quite often it's called the conditional probability law. Axiom 4 is really profound. It's the only one of the axioms, only one of the four, that can also be written in terms of probability density functions or uncertainty models. That's kind of nice. And the import of that you'll see in a few minutes. For example, you can have the probability density of x and y equal to the probability density of x given y times the probability density of y. Or you can have combinations of probability densities and probabilities. You can have the probability density, the joint probability of joint probability or joint uncertainty model of x and y is equal to the density model for x given y times the probability of y. Or vice versa, you can have the probability of x given y times the probability density of y. You can write it in any of those terms. Now, the reason why mathematically I throw out to my audiences that are mostly engineers, I throw out the fact that this is due to the fact that in L2 vector spaces, which is how we model the real world, both the differential and the integration operators are linear. So I like to throw out that technical blurb, but the point is that mathematically we can indeed write that fourth axiom, the conditional probability law, in terms of probabilities and probability density functions and combinations. It's very useful. So that's a little more on axiom 4 for you, and we're going to use that just a bit more. As I mentioned before, the commutativity of the Boolean and in axiom 4 leads to something very useful. Now, I just gave those two terms as stated in probabilities. Let's apply just a little bit of algebra. We're going to divide both sides of that equation by the probability of B given H. Now, that wasn't really complicated. Many of you may or may not recognize what we just derived. But what we just derived is formally called Bayes' law. I don't make a big deal out of Bayes' law. We use it in all probability. It's very, very handy, very, very useful. And suppose there's some insights available. Suppose A is our proposition we're considering, the outcome levels that we might realize, and B is our data and information that's available. Let's rewrite it in those terms. We have the probability of A given our data is equal to the probability that we got our data given A times the probability of A divided by the probability that we got our data. Now, an interesting thing, that last term you see in the denominator, the probability that we got our data, well, it's just a number. We don't know what that number is, but because of the first three axioms, we can actually calculate that number if we want to, if we have the other terms, because we know that the total probability has to be equal to 1. It's a normalization term. And we could conveniently, as a result, simply write the conditional probability law as a proportion. Probability of A given the data is proportional to the data given A times the probability of A. And of course, we can do that with density functions as well. So I wanted to show you that. Now, there's some significant import to this. The insight that we've got, taking that particular equation, the first term on the right of the proportion sign is called the likelihood function. If you've ever done maximum likelihood estimation, you're using the likelihood function. It is the probability or the uncertainty model for getting the data that we got, given the possible values of that outcome that might be realized. If we have that uncertainty model for our risk, we can always formulate. Now, it's important that we be able to formulate and write it down because we're going to have to code things up. But if we've done our analysis properly, we're going to know what that uncertainty model is. And, in fact, you can use that for any and all types of data. And when I talk about that, the distinguishing point that I want to make is most people are used to, from their probability statistics courses, using actual observed data. But there are other types of data. For example, and you will see this in session 3 in spades, there are censored data. The fact that something did not occur. There's a lot of information in that. And that's very, very important. That's called censored data. So we can actually formulate the likelihood for both observed data, censored data. We can actually formulate the likelihood for using expert opinion or an assumption as actual data in a state-of-the-art quantitative risk assessment. So we can always do that. That's always available to us. The second term on the right of the proportion is called the prior, probability of A. In other words, probability that we get some realization, period. Well, the fact of the matter is we usually have no earthly idea what the model should be today. Just literally don't. And there's no reason to, because we don't have any functions. We can't do any analysis. Okay? We just don't. And of course, if we're going to guess as to what that is, that just puts us back into qualitative risk assessment. So why bother with all this math stuff? If we're going to be guessing anyway, it's a whole lot easier just to not even bother with this prior thing. What would be best for us to do, considering that we don't know what to do, is to be completely objective about it. Okay? Instead of guessing. If we're completely objective about it, then whatever we have as results are going to be objective results as well. In other words, we haven't tainted anything with a guess or an opinion. All right? Now, the question may arise is, how do you be objective? Or how do you come up with an objective uncertainty model? Well, we can be objective. Methods from information theory have been developed to create objective uncertainty models for a particular problem. In fact, we can derive those models based on 3 different techniques from information theory. The first method was developed by Sir Harold Jeffreys in 1939. And that method is to find the model for the problem that minimizes the Fisher information for the problem. Now, the Fisher information matrix tells us how important the information is. So if we minimize the information provided by that model, by the prior that we have to use, we are being as objective as possible. It's a simple optimization problem. Sir Harold Jeffreys developed this technique back in 1939. Okay, but it minimizes the Fisher information. The second method was to find the model that maximizes the information entropy for the problem. Lindley and Savage, the father of Sam Savage, who was also presenting during Risk Awareness Week, developed this back in 1971. And entropy as a measure is a measure of disorder. So if you maximize the disorder, information disorder provided by this model for the prior, then you're obviously the most objective that you could be. The third method that's been developed finds the model that maximizes the expected value of perfect information for the problem. Bernardo and Smith developed this in 1995. Now, the expected value of perfect information is a measure of how much value could possibly be added as if you had absolutely perfect information. Clearly, if you find the model such that perfect information maximizes this value, you're obviously the most objective you could possibly be. And Bernardo and Smith developed this. Now, the really interesting thing is I've gone through derivations for a number of problems all three to see what particular model I come up with for an objective uncertainty model for the prior. And in every case I've run so far to date, all three methods produce the exact same uncertainty model for the same problem. I don't know about you, but that's extremely reassuring to me. Three different approaches to how you would be objective, how you would optimize objectivity. And in each case, or maximize objectivity, in each case you get the same model. That says that there's got to be some real solid base to this information theoretic methods that we have. So the point is that we can indeed be objective about those priors. The objective priors actually give us a worst case information setup for our problem. And if we can make a good decision based on that worst case information setup, we've got it made. There's no need to do the math and derive all of these. I've done it because I come from a physics and math background, so therefore this kind of thing is fun for me. They're all tabulated and available in the textbooks. In fact, Bernardo and Smith has a great table for most of them that you would ever possibly need. So you don't have to do the mathematics. Just develop your problem and look them up. Very, very easy. And we can be objective. Very easy to do today. Also, if in your analysis you've got uncertainties about what the causal model actually is, you can use these objective uncertainty models. Be objective about what the causality actually is. This is another thing that can be done in your risk analysis phase, where you're analyzing what the causalities and the sensitivities are. So that's something that's not used quite a bit, but it's extremely effective. Interestingly enough, working with Kalman filters for space probes and space missions and things over the years, we've actually been doing that. They're implemented. Most people don't recognize that. But where we have uncertainties about what the causal models are involved, we actually can use some of these objective models instead of making a guess on what the causality is. That's really nice, because if you get a good answer, and we have, because we've had numerous successful space missions. The latest, of course, is the Horizons missions to Pluto. That's a long ways out there. So name dropping, I know Alan Stern, who ran that project. He was in graduate school with me. But in the event, that's something that has been done. It's used all the time in Kalman filtering. Now let me throw something else in. I invented this term pseudo-ignorance priors because quite often when you use an objective prior, what you get is you get an integrand and uncertainty model that's analytically intractable. And that analytically intractable integrand doesn't work well with the numerical methods we have to integrate to get our probabilities. So in those cases, we get a problem. The problem is the fact that the integrand is improper. What that means is that the integral will go to infinity. It won't be a definite integral. So we got problems with that. That obviously violates the third axiom of probability, since the total probability has to be 1. So when we have an integral that goes to infinity, we've got a problem with our models. But we can address that, and by using a pseudo-ignorance prior, such that the numerical methods will work. Usually the integrand is improper, almost always it is. And we can create what I call a pseudo-ignorance prior, and we use what I'm calling engineering judgment. It's the understanding of the causality, the analysis process, the judgment of the problem, where we actually truncate the objective prior at some appropriate point, or at appropriate points. You may object it, may truncate it at both ends. And of course, when you truncate it, that makes the integrand proper. And of course, the numerical method stabilizes and works properly. Let me give you an example of what I'm talking about with a pseudo-ignorance prior. This example is a vehicle reliability test using the Weibull model. Now, for reliability, if we believe, have no reason not to believe, rather, applying Occam's razor, that we only have a single failure mode involved, the Weibull model is wonderful. It is the most general, one-sided, unimodal model that there is. So the Weibull model is an ideal when we're talking about reliability and testing for reliability. So that's the reason why we're going to use this. Our concern is that we've got a reliability requirement of 95% at 100,000 miles. We're worried that we're not going to meet that reliability requirement. And what do? We go run some tests, okay? And we end up with failures or survivors, cases of where we tested maybe to the length, say the test was 200,000 miles of driving. We drove for 200,000 miles. If we don't have a failure, that's a survivor, a censored data. The key is that we're really uncertain about the Weibull parameter eta. Eta is the scale parameter for the Weibull model. And we know that if eta is greater than 269,145 miles, that our reliability requirement is satisfied. In other words, if eta is greater than 269,145 miles, we know that we have 95% reliability at 100,000 miles. But if we're uncertain about eta, we're uncertain about a reliability requirement as well, satisfying it. In this particular example, you want to use an objective prior model. We use the Jeffreys prior, which is the same as the maximum entry prior, same as the reference prior from Bernard Rhodes Smith, which is sent for that scale parameter for the Weibull, which is simply 1 over the scale parameter, or 1 over eta. What this does is it produces an analytically intractable and improper integrand. We can't integrate it to get the probabilities we need to answer that question, to find out how sure we can be, given our data, that our reliability requirement of 95% at 100,000 miles is satisfied. So we've got a problem. And it turns out that because it's an analytically intractable and improper integrand, our numerical method fails. It doesn't stabilize. And we'll talk about that in great length, the numerical method in specific. But it just doesn't work, won't work properly. We can't use it to calculate our probabilities. So what we use is a pseudo-ignorance prior. And to do that, we simply truncate the Jeffreys prior way out at the far right end. Say, for example, at 1,000,000 miles. Very rare to hear of a vehicle that goes over 1,000,000 miles. It's even rarer to hear that a vehicle manufacturer will warranty past 1,000,000 miles. It's not uncommon to see vehicles warrantied out to 100,000 miles, especially for the drivetrain, which is why they have a reliability requirement like that, is so they can set their warranty cost. So the solution in this case is truncated out at some far out point. Well, the question is will the numerical method stabilize? Now, first off, let's look at the engineering judgment involved here. It's very reasonable too. If the requirement is actually satisfied, the reliability out at 1,000,000 miles is 10 to the minus 23. It's negligible. Totally small, extremely small. Can't even measure it. So it's very reasonable. The question is will it stabilize? Well, it turns out in this particular case, even with this exaggerated truncation, which now gives us a proper integral and a proper integrand, the numerical method stabilizes, gives us a probability. Sure, we got an error out there in the 10 to the minus 23 range, but I don't think that's going to affect anybody. Even in a really serious safety situation, you're not going to be worried about an error on the order of 10 to the minus 23. So this is an example of using a pseudo-ignorance prior. As I mentioned earlier, I'm really focusing on applications, really finding ways to get problems solved. I'm not trying to lecture you on theory, but all of this is directly applicable. And we have to come up with some ways to apply good theory to make it work. We have to do what I call engineering. Now, I've talked about numerical methods. Let me talk about numerical methods in a little bit more detail. I think this is important because we need to understand what we're doing. In a lot of my work, I've done a lot of development of numerical methods over the years. I've built integrators and things like that for spacecraft. Back in the days when CPU and CPU power and memory were measured in K rather than gigs. So numerical methods are extremely important. The one numerical method that we use to numerically integrate things is Monte Carlo. And I mentioned earlier that up until the mid-1990s, it was impossible to solve those integrals for real-world problems, to do a quantitative risk assessment. And of course, if it's impossible to solve those integrals, why should anybody possibly ever teach it? And nobody has. However, in the mid-1990s, there was a technique, a numerical method called Markov chain Monte Carlo. It was fully developed, implemented such that we can use it, the algorithms work, and now we can solve any integral we can formulate. It's absolutely amazing what we can do with Markov chain Monte Carlo. So let's look into it. Before I get into Markov chain Monte Carlo, I really want to explain Monte Carlo first. There's a lot of misconceptions about Monte Carlo. You often see terms Monte Carlo simulation or Monte Carlo run. There are other things. But Monte Carlo is really just a simple numerical integration method. It approximates an integral, nothing more. And if you look at it properly, it is a series expansion. Almost all of our numerical methods come from series expansions. It's really nothing more than that. People need to realize that. People think that it's a simulation. The Monte Carlo is run on a simulation. The simulation is the integrand. The Monte Carlo is run to get the integral that you need. And of course, that's just what we need to approximate a probability, because a probability is always an integral of a probability model or an uncertainty model. Just exactly what we need for a risk assessment, a quantitative risk assessment. Also, Monte Carlo could work with integral transforms. Many of you have probably heard of Laplace transforms or Mellin transforms or let's see, what other transform? Laplace Fourier transforms. Well, there are all sorts of integral transforms that don't have formal names, mostly because they have analytically intractable integrands. But it works for any sort of integral transforms. And in our analysis, we are going to do some integral transforms. Some of them look pretty ugly, but we can use Monte Carlo to solve them. It's extremely powerful. Those of you who are familiar and have used Monte Carlo realize that it's extremely powerful. A lot of tools out there to do it, but those tools are doing what I refer to as ordinary Monte Carlo. We'll talk about that in a minute. Monte Carlo is easy to use. In fact, it's so much easier, and I'll show you an example in a minute, where it's a whole lot easier than trying to figure out the problem. It can be very accurate. However, as with all numerical methods, there is an inherent error, inherent numerical method error in using Monte Carlo. Now, I have developed a technique where that error can be bounded within a certain level of risk. And using those bounds, you can still make a very, very effective decision, even with a small number of samples. If you want some information about that, I haven't formally published this yet, but I'd be happy to share it with you because it's extremely useful. So there are ways to bound that. There are people who are unaware that there are inherent errors in the Monte Carlo numerical method. I know an individual PhD who's developed wonderful tools for doing Monte Carlo, ordinary Monte Carlo, probably one of the best that's out there. But this person with their PhD who developed a tool to perform Monte Carlo didn't understand the reason why we get varying answers, which are the inherent errors in the numerical method time to time. In fact, that person has recommended to people that they just use the exact same seed to avoid the variation, which of course accomplishes nothing. That really compounds the error. But the point is a lot of people, even some real experts in Monte Carlo, aren't really aware of how those inherent numerical method errors work and the sizes of them. And they can be quite large. Now, ordinary Monte Carlo requires that you generate samples using either a built-in random number generator, that could be a pseudo-random number generator, a quasi-random number generator, or it can be a grid if you want. You don't have to have random numbers. You can just use a grid and perform the Monte Carlo calculations to calculate an interval. Brian Hayes had an excellent article in American Scientist a few years back about I think the title of it was Quasi-Random Ramblings. And it was about comparing pseudo-random number generators with quasi-random number generators for Monte Carlo calculations. And one of the things, he gave a beautiful example of how to calculate the area of a leaf. His daughter asked him the size, what the area was of a maple leaf. So he created a simple grid on a light screen, put the leaf on top. He knew the total number of points on that grid. He counted the number of points inside the leaf. He knew the total area of the grid, divided by the total number of points, and had the area of the leaf for his daughter, out to a certain error. Okay, and of course it's pretty obvious. You can move that leaf in different positions and get different answers, which is the exact same thing that you're going to get with different random number sequences. So ordinary Monte Carlo requires generating samples using built-in random number generators or grids. Grids are usually not used because the problems are too complex. You usually have to have n-dimensional grids for most problems in the real world. Let's give a simple example of Monte Carlo so everybody can understand why we go to it and use it. Suppose you have a problem where you're firing an arrow at a target with a 1-inch bullseye, and you want to know the probability of hitting that bullseye, and that you have modeled as the uncertainty in each x and y coordinates of where your arrow is going to land using an independent standard normal distribution. This is an idealized textbook type, classroom type example. We need to solve an integral. We need to solve the integral, the probability that r is less than 1/2. And we have an uncertainty model for the probability of what the range is from the center of the target. But we know that the range from the center of target is equal to the square root of x squared plus y squared. And we have modeled our uncertainty about x and y, where it's going to land, as standard normal distributions. Now, we can analytically express this integral in a two-dimensional integral over x and y. We can do that. That's second-year calculus. And plug it in, and plug in these uncertainty models for x and y into that, and potentially solve it. I will tell you that it's a pretty complex integral. If I was going to bother to write it down, we have to calculate the Jacobian matrix, take the determinant of that, and end up with a two-dimensional integral. That's doable. It's extremely complex. It makes an ugly one. I'm not even going to bother to write it down, because if you know where I'm going with this, it's very easy to solve using Monte Carlo instead of going through all that math. Easier with Monte Carlo. Excuse me. Let's get, say, for example, 10,000 samples for each x and y from a standard normal. Now they're independent, so we just get 10,000 samples for x and 10,000 samples for y. We apply the equation r equals x squared, square root of x squared plus y squared, to the sample pairs. This gives us 10,000 samples of the distance from the center of the target, r. That's interesting. That's pretty simple to do. What have we actually done when we did that? The next step, obviously, is to count the number of those samples of r less than 1/2 and divide by 10,000. That tells us the probability that we're going to hit the bullseye. Now, it turns out this problem has an analytical solution. Okay, and what that analytical solution is out to 7 decimal places, 0.1175031. Reason why is we know that r is distributed with a Rayleigh distribution, and we can integrate a Rayleigh distribution. I'm not telling you this, but instead of going through all of that and trying to figure out how to do it, we can use this Monte Carlo technique, 3 simple steps, and get our answer, or get an approximate answer. So let's look and see what the code is. I'm going to show you code in R. If you have not looked at R, R is a reverse engineered version of a commercial product called S+. The author of S+ actually wrote the user's manual for R. R is free. Single user license, last time I looked, of S+ was $6,500. So R is a really good buy. It's free. It's extremely powerful, and if for no other reason, it's good to use as a desktop calculator. Okay? So to give you an example in R how we would do this, the code is simple. You'll see the first 2 lines. We get our samples, R norm is the function that gives you the samples of a standard normal. And then we have that one-line conversion from all of the x and y's into all of the r's. R is replaced by the square root of x squared plus y squared. We zero a counter to 0, and then we go through a for loop, a loop that counts. If it's less than or equal to 0.5, we count it. Then we divide the count by 10,000. Exactly what I showed you in that simple algorithm. What have I got there? 6 lines of code to get an answer. Very, very simple. 2 of those lines are just to get samples. Very simple. We get 0.1148. Please note that we only got 4 digits in our answer. If we repeat this code multiple times, which I did, I got 4 other answers. They range from a low of 0.1142 up to a max of 0.1213. So they bracket the real answer. Remember, Monte Carlo is only approximate. Now, how good the approximation is a function of how many samples we used. Okay, we'll talk about that. That's the inherent numerical method error that we're talking about. More samples reduces it, reduces the variation in the answers. That's always good. Sometimes it's very expensive to obtain more samples. Sometimes we could still make a very, very effective decision, and you're more than welcome to contact me about that method to bound the numerical method errors. But in this particular example, if in order to take the shot, we only needed to be 10% sure after getting 5 answers, very, very easy, very, very quick to do, that are all greater than 10%, it might be good enough to decide to actually take the shot. But we don't know. The true answer might be less. In fact, for using 10,000 samples, we can be off. The true answer obviously is 11.75031%. We could be off by as much as 0.4% in our answer, plus or minus with 10,000 samples. That's a larger value than most people realize. And that might affect, depending if we got the really, really low answer, 0.1142, and subtracted 0.4%, that'd put us back at 0.11. Have to be careful with it. So it may be good enough to decide. Very, very easy, very simple. A whole lot simpler than working through that second year calculus course of developing the Cartesian to circular components, coordinates. Now, there's some limitations of ordinary Monte Carlo. We've already talked about the numerical method errors. First off, you can only use built-in samplers with ordinary Monte Carlo or a grid if you want to create that grid. As I mentioned earlier, most of our problems, complex n-dimensional grid is too difficult to do. These are almost always univariate. Our samplers are almost always for a single variable. Most of our problems, our risk problems in the real world, are multivariate. The built-in samplers restriction to ordinary Monte Carlo almost always requires we make assumptions. And what those assumptions typically are guesses on what the parameter values are. Say if you're using a normal distribution. Say you know you've done the analysis and you know that the uncertainty model should be a normal distribution. You have to choose what the mean and the variance, the parameter values are. Well, you're uncertain about those. But if you just guess at a number, you have to guess at a number for those to be able to use ordinary Monte Carlo, or else you won't get an answer. Every single Monte Carlo tool out on the market requires that you make such guesses. Every single one. So what that boils down to is you've just got sophisticated qualitative risk assessment if you use an ordinary Monte Carlo tool. Okay? Our answer precision. If you recall, I told you to note that we only had 4 digits of precision. You might have thought that was because of R. Well, no, it wasn't because of R. It was because we only had 10,000 samples. With 10,000 samples, we only get 4 digits of precision in our answer. So the number of samples, for example, if we only use 100 samples, we're only going to get 2 digits of precision. If you think about it, it's real easy. If you only use 100 samples, your answers are going to go from 0 to 1%, 2%, 3%, 4%, all the way up to 100%. So you get 2 digits of precision. So our answer precision is limited by our number of samples. And smaller sample sizes can greatly increase the inherent numerical method errors. For example, with only 100 samples, the numerical method error for ordinary Monte Carlo, or for Monte Carlo in general, can be as much as plus or minus 40 percentage points. Your answer is always going to be between 0 and 100. But if you get an answer of, say, 80%, the true answer could be 40%, or it could be 100%, anywhere in that range. So the number of samples is extremely important. Now, if you can bound those errors, you may be able to still make a very, very good decision. So, and as I said, you can contact me for information about that. Monte Carlo inherent numerical methods can be bounded and enable good decisions. Contact me. Now let's talk about Markov chain Monte Carlo. This was the development that occurred in the mid-1990s. The only difference between ordinary Monte Carlo is that the samples are generated by a tuned Markov chain instead of using built-in samplers. Now that Markov chain, as opposed to the built-in samplers, can be multidimensional, which is very useful for real-world problems. You literally, with Markov chain Monte Carlo, could sample any integrand you could formulate, and as a result, get an approximate value for any integral. In the literature, I have seen multivariate problems where they had up to 20,000 correlated variables sampled with Markov chain Monte Carlo. Now, I'll be perfectly honest with you, I've never run into a problem with that many. I've run into problems with maybe 100 correlated random variables, but never 20,000. But it's been done. So you can sample that would be 20,000 integral signs followed by an integrand of 20,000 variables with 20,000 d variable 1, d variable 2 at the end of that integral. Pretty complex. You can have complex combinations of discrete and continuous random variables that you can sample with Markov chain Monte Carlo. Now, Markov chain Monte Carlo, just like ordinary Monte Carlo, is still subject to the same precision. If you only have 10,000 samples, you're only going to get 4 digits, and also the same numerical method errors that apply to ordinary Monte Carlo apply to Markov chain Monte Carlo. As I say, the only difference is the samples are generated by a tuned Markov chain. So it's really kind of a misnomer to call it Monte Carlo. It should just be Markov chain random sample generation. Get the same accuracy issues with ordinary Monte Carlo, the numerical method errors, and the precision. Markov chain Monte Carlo has a few drawbacks. One is it does require manual tuning. This is not something you can build in a tool, unfortunately. And you have to pretty much code it up separately for every risk problem. Every risk problem is unique. You really can't build any general risk packages to do Markov chain Monte Carlo. For some specific types of problems, very, very general types of problems, you can. But you can develop a general package, but it's a very, very limited set of problems. In general, every problem you'll have to code it up yourself. Fortunately, it's not that horrible to code out. The algorithm, let's go through that algorithm. Now, obviously, to start, you have to formulate the integrand that you want to calculate an integral for. That's more important. That's important for any kind of risk assessment or any kind of probability you want to compute. Second thing is you select a proposal step size for the variables of integration. I'll explain this proposal step size in just a second. So you select a value. Also, you start at some point, some legal value in the range of the integral. Okay? You just set it. Okay? Because you're starting off a Markov chain. That's what we're doing. If you don't know what a Markov chain is, I probably should have explained this last slide. The simplest Markov chain is called the random walk. And the example we use for the random walk is a drunkard's walk. If you had a drunk standing on, let's say, on a number line and he's at 0, and there's a 50% probability he's going to take a step to the right to position +1, or 50% probability he's going to take a step to the left to position -1. If you let the drunk go, eventually he will cover the entire number line. But every step that he takes, the probability of where he's going to be is dependent on the previous step. For example, if he's at step 4, he'll either go to step 3 or he'll go to step 5. That's a Markov chain. Now, normally, I did a whole lot of work in my career working with simulating noise for, say, sonar and anti-submarine warfare. And in simulating noise, we use pseudo-random number generators, and we wanted each sample to be independent because the noise had to have certain characteristics. It had to be like ocean acoustic noise. And so it was really important that the samples that we generated were independent sample to sample, which is what you get out of a pseudo-random number generator or a quasi-random number generator. But you don't get that with a Markov chain. Markov chain, each sample, from sample to sample, there's correlation. But since all we're doing is calculating integral with it, who cares? It really doesn't make any difference. So that's what a Markov chain is. Simplest one, like I said, is a drunkard's walk. Now, if the drunkard could take any size step to either side, you really get a nice balance. You cover the entire number line very, very quickly. So we start with any legal value for the variables of integration, and we repeat the following loop to get new samples, all of our new samples. We propose a new sample. The proposed new sample starts with our first sample, and we add something to it. Typically, we get a sample from a uniform distribution from the negative side of our step size, our proposed step side, to the positive side. This is just like the drunk taking a step. D theta would be 1 in the case of the drunkard's walk. And that would be our proposed next step. Now, this algorithm is going to be a bit astounding, but it works. I doubted it for years. The next step is we want to take a logarithm of the ratio of the integrand evaluated at the new sample divided by the old sample. And we take the logarithm of a division. It turns into the logarithm numerator minus the logarithm of the denominator. So we have our ratio, which is the evaluation of the integrand that we formulated. Okay? Next step is we take the logarithm of a sample from a standard uniform distribution. Uniform distribution going from 0 to 1, and we take the logarithm of that number. Next step, if the logarithm of that uniform sample is less than the logarithm of the ratio of the integrand evaluated at the proposed sample over the integrand evaluated at the current sample, we choose to accept the proposed sample as the next sample. Otherwise, we set the new sample, the next sample, to the current sample. Now I know what you're thinking, because I went through this process. I thought, wait a minute, you didn't change. It's the exact same number. How could that be a random number generator? Remember, we're working through a Markov chain, and we're going to cover the entire number line or the entire space or the integral, depending on the dimensions of it. And other dimensions may move, but this one doesn't. Or it may be that we're going to have to hit certain points multiple times to have that integrand covered at the right levels at every point in that space. I had great difficulty with this algorithm, and I tested. In my statistics classes, I go through with my students and have them prove to themselves for problems for which we know the analytical answer. We go through ordinary Monte Carlo where they use a pseudo-random number generator to generate it. They get the exact same quality of answers using this algorithm as they do from a pseudo-random number generator. So they prove that to themselves such that when they work with a problem that has no built-in random number generator, they can then trust it. But it does produce a complete set. Okay? That's the algorithm that we need to code up for every problem. Of course, the key has to do with the formulation of that integrand. And we have to do that from our problem analysis of the causality and of also the sensitivities in that. And of course, we have to identify all the random variables. Now some notes on the Metropolis Hastings algorithm. This capital theta can be a vector of variables of integration. Okay? It can have a lot of dimensions, and it can be just a simple vector. We can have integrals of vectors. We can have integrals of matrices. A lot of people, that stuns a lot of people, that we can have integrals of vectors and integrals of matrices. In fact, we have probability distributions that are distributions of matrices. The Wishart, for example, and the inverse Wishart is a probability uncertainty model for matrices. That usually stuns a lot of people, even a lot of engineers that work with matrices all the time. We could propose either an entire new vector one at a time and test for acceptance of the new vector, or we could test for, and of course in that case, our step size is, a proposed step size is a vector, and also our proposed step, our proposed change is a vector, or we can add an internal loop to propose each new variable one at a time and test it for acceptance to get a new sample vector. Each sample of the vector is a sample of the integral space, regardless of how you get it, in proportion to the joint integrand. So when you get enough samples, you can calculate the integral, excuse me. We can use other models for proposals besides that, that uniform, from minus proposed step size to the positive of the step size. In fact, one that's very, very commonly used that works great is a normal distribution with the mean at the current state, and the step size is effectively replaced by the variance. So we can vary the variance. That gives us a different proposal to add to our previous value. And if we choose, after we get all of our samples, if you scatter plot one variable against the other, you're going to get a really interesting plot, which will show the correlation, or what we would call a marginal joint density, marginal uncertainty model for that variable against the other variable. That's really helpful. Those are interesting to look at. They never, for real world problems. Look, most of us normally think of a nice ellipse because we're used to Gaussians. But real world problems don't use the normal distribution. That's a dirty little secret a lot of people won't tell you. The set of samples for a single variable give us actually the marginal distribution for that variable. Okay? In other words, we can look at that by itself. And that is as if we have taken that integrand and integrated out all of the other variables. You'll notice here, this is the uncertainty model, or the marginal distribution for theta sub I, and you'll notice right there in the middle of all the integral signs, we're missing theta sub I. And you'll notice out with all the differentials, we're missing d theta sub I. So if we integrate all the rest of those out, we're left with the uncertainty model just for theta. And likewise, you'd actually, in other words, this complicated integral is given to us just by looking at that one set of samples. Likewise, if you integrated out everything except for 2, you would have the uncertainty model for theta j and theta k. Okay? So that's pretty nice. That's really, really nice to be able to see those things. Those things usually provide us insight into our problems. Now, as I mentioned before, one of the downsides to Markov chain Monte Carlo and the Metropolis Hastings algorithm is that you have to tune it manually. This is not a process we can implement in a tool. It's something we have to build, and we have to manually tune it. Trial and error and subjective judgment is all that's needed. Turns out Danny Gammerman, one of the references that I did, actually went through the mathematics in his book and proved that subjective judgment, the right kind of subjective judgment, is all that's needed. So we don't have to go through any mathematics to prove that we have a nice, stable Markov chain. To tune this algorithm, the Metropolis Hastings algorithm, we have to collect data on the numbers of proposed samples that were actually accepted. We actually need to calculate the acceptance ratio for each variable, okay? Either on the entire vector or each parameter at a time. The acceptance ratios that we're looking for, practice has shown us that they should be within the 30 to 60% range. And if not, you're going to want to adjust. Our adjustment thing is the proposal step size. And then we look to see at the samples if they really look like noise. Everybody knows what noise looks like, okay? Everybody has seen the movie Poltergeist with the noise that was on the TV. Well, we know what noise looks like. If the ratio, it turns out that we get, the acceptance ratio is too high when we run our algorithm, the samples are going to show tracking, which we don't want. And to combat the tracking, we increase the step size, our proposal step size. If the ratio is too low, less than 30%, the samples tend to get stuck. And to solve that, we decrease the step size. Not necessarily, I mean, we can see a consistency in what you do, but it doesn't necessarily make sense to me. It didn't make sense to me from the very beginning. I will tell you my personal preferences are to get acceptance ratios in the 50 to 60%. Just naturally, that makes me happier. But that's a subjective personal thing. Anything in that range, 30 to 60%, usually is good. We need to look at the burn-in because the Markov chain is going to take a while before it gets stationary. And what I mean by stationary is the statistics are constant from throughout the rest of the chain. Okay? In other words, if you took a chunk, multiple chunks of samples, you should get very similar means, variances, etc. So you have to look at the burn-in. And what we do is we truncate. Let's talk about tuning by eye, the Markov chain. Let's say we got a chart like this, and our acceptance ratio was 0.9. As you can see the samples tracking up and down, up and down, up and down. Doesn't really look like noise. So we increase our step size to address this. Let's say we increased it a whole lot, and we get an acceptance ratio of 0.1. Well, clearly we see that this doesn't look like noise, and you can see that samples get stuck at a single point. You know that the sample to sample, you can have the exact same point. In this case, you can see a lot of straight lines, which indicate a lot of getting stuck. So to combat that, we decrease the step size. We find the right step size, and we get an acceptance ratio, let's say 0.53. Well, guess what? It looks like noise now. That literally looks like noise. Now, that's only 1,000 samples, and it's spread out. So we do some funny artifacts. You might see a little tracking here and there, but it's really hard to pinpoint. So we've got a suitable step size, and it looks like noise. Danny Gammerman proved that by looking at this and getting the acceptance ratio right, we've got a stable Markov chain, or we have a tuned Markov chain. We talk about convergence to stationarity. Scatterplot, you want to scatterplot your samples to identify the point at which it becomes stationary. And what we do is we just eliminate those earlier points. We use samples beyond that point. This is called burn-in. Now, there's some solutions about it. Here's an example here. We started off up at around, it looks like around 2,000, 2,500 is where we started the Markov chain. That's in the legal range. Okay, you'll notice it's way, way out of the range, and we don't have any samples in those 10,000 that get anywhere close to that. But you'll notice the Markov chain does track down into a region of stability. In fact, after 1,000 points, we know it's stabilized. It has converged. So let's look at just those 9,000 points to the right of the 1,000th point. Well, it looks like noise. Now, the scale changed here quite a bit, but that's good for us because it looks like noise. Those 9,000 samples look like noise. Still don't have anything up around 2,500, but it does look like noise. So we have burn-in. Now, one of the things is if you start your Markov chain down in that region where you have stability, let's say you go through this process and go, ooh, 2,000 is not a good point. Let's start instead, say, around 200. We may get a chart right off the bat that looks exactly like that, and solver integral may not have to remove any burn-in at all. In fact, I usually don't, because whatever errors I'm going to get, the inherent numerical method errors are going to be much larger than whatever error due to a little lack of stability. But that's convergence to stationarity. Let me give you some heuristics. I've used short chess chains. In other words, if you're going to tune, use 1,000 to 3,000 points. 10,000 points if it runs very, very quickly. The data means, if you can take the mean of the actual event data or observed data, they're good starting points for a quicker burn-in. Okay. 2 standard deviations of the data, the event data, are really good first proposal step size. You just don't come up with it out of the clear blue sky. You can. I find that variable by variable and inner loop acceptance testing is easier to tune than a vector at once acceptance testing. It's just hard because you have to change the proposal step size on all the elements at once. And that's tricky. Beware, however, if you use an inner loop, variable by variable acceptance testing, changes on the proposal step size for one variable are going to change the acceptance ratios for the other variables. So you still have to check them all. And with lots and lots of variables, that may be a lot of checking. Improper integrals, strangely, can show nice stationarity in short chains, maybe 1,000, maybe 500 points, and then track off in a longer chain and then come back, just stationarity. Here, of course, the thing is to go ahead and use a pseudo-ignorance prior to get rid of those track-offs. But that does happen quite often. Sometimes an improper integral actually becomes stationary really, really well. Quite often that happens. It's not a given thing if you have an improper integral that you have to go to a pseudo-ignorance prior. But a pseudo-ignorance prior can help you. This completes this particular session. We've talked about, you've seen more of the thinking involved because we started thinking about the actual applications. And we've gone through the math, which is actually quite simple, other than the actual math involved in the setup of the problem, in understanding the causal models that are developing the causal models and understanding the sensitivities. You don't have that much math to do. The coding is relatively simple. That Metropolis Hastings algorithm is very, very easy and very little code to actually use. And then, of course, the Monte Carlo calculations using those samples are very simple. So there's not a whole lot of coding. You can code in any language you want. I happen to like R right now, but Lord knows I've done Monte Carlo simulations and Markov chain Monte Carlo simulations and things like BASIC, Fortran, Forth, R, MATLAB. Let's see what else I've done it in. Mathematica. Just about any language you can come up with, you can use. R is a real nice one. It's free. And as I mentioned to you, it's nothing. If you download it for free for nothing more than a desktop calculator, it's great. Our next session, I want to remind you, you may want to go and look at the replay of session 1. It might give you a little bit more context for this session you just watched. But session 3, we're actually going to go through the process and the steps to perform a state-of-the-art quantitative risk assessment. And I'm going to provide some real-world examples. These real-world examples are complex. They come from aerospace. The reason why they come from aerospace is I've worked a lot in aerospace. But the kinds of things that are done and the problems that we run into, the modeling is no different than what you find in financial sector or any other sector in the modeling. So they're all translatable. And I welcome you to session 3. I want to thank you for your participation. Here's my contact information, email address, there's my phone number, website, tons of resources. My website is primarily a resource set for people more than anything else. And if you'd like to connect with me on LinkedIn, I get involved in a lot of discussions on these topics, a lot of the conceptual topics, and a lot of the ideas, a lot of the things that we can do today. There are a lot of people who are so unaware of what we could do with state-of-the-art quantitative risk assessment that they just don't believe it can be done. But of course, you know what they say, the aphorism about those who say something can't be done should get out of the way of the people doing it. Well, I'm going to show you how to do it yourself, and you'll be one of those people. And here's a set of resources that I use. I think we see Danny Gammerman is about 8th down the row that I've talked about. He's got the like I say, the mathematical proof that stabilizing a Markov chain, you can do it. The tuning a Markov chain rather can work by your subjectives. Thank you very much for your participation. I look forward to seeing you in session 3. Thank you.